Okay, here we are back again with Chapter 14, Review Exercises, Part 2. If you haven't seen Part 1 yet, please go back and find the Part 1 video. Part 2, beginning with number 23, I believe. Unless I messed up on the cutoff point here. But I think that's right. I'm on page 27, number 23. Your friend says that the buoyant force of the atmosphere on an elephant is significantly greater than the buoyant force of the atmosphere on a small helium balloon. Is it possible that the buoyant force on an elephant is greater than the buoyant force on this helium balloon? Well, what's the buoyant force equal to? Is not the buoyant force equal to the weight of the displaced air? Just like in a liquid, the buoyant force is equal to the weight of the displaced water. In air, the buoyant force is equal to the weight of the displaced air. Now, which one displaces more air? The helium balloon or the elephant? Yes, the elephant displaces far more air. So that means that the buoyant force on the elephant is far greater, incredibly greater than the buoyant force on the balloon. Then that's really stupid. Why don't elephants float away then? I think you're crazy, Mr. Peer. Oh, wait a minute. Here's the problem. This helium balloon actually weighs less than the displaced air. So there's more buoyant force than there is weight of the balloon. Therefore, it rises. But with the elephant, yes, he is displacing a massive amount of air, which has a pretty hefty weight to it. How many kilograms of air does an elephant displace? I don't know. But he still weighs far more than the weight of the air he displaces. So if he weighs far more than the weight of the displaced air, even though he displaces far more air than the balloon, he weighs a lot more than his own displaced air, so he goes down and is able to stand on the ground. What happens if you were to step into a vacuum chamber, like the world's largest vacuum chamber? I think I showed you the video once a long time ago. You step into that world's largest vacuum chamber, what happens? Well, yeah, you die pretty quickly. Suppose you stepped in there wearing a spacesuit. That would work. Yeah, that works. That's what spacesuits are for. So you step into a vacuum chamber wearing a spacesuit. Okay, cool. What happens to your weight? Well, in the vacuum, do you have a buoyant force? The buoyant force is equal to the weight of the displaced air. If you're in a vacuum, how much displaced air is there? None? That's right, none. There's no air to displace. You're not displacing anything in a vacuum. Therefore, there's no buoyant force. Therefore, you would weigh a little bit more. How much more? Equal to, you would weigh more to the tune of the amount that you would normally displace of air. How much does my displacement of air weigh? I don't know. Some fairly small fraction of a kilogram, some fairly small fraction of 10 newtons. I don't know how much my displaced air weighs, but I step into a vacuum, that's how much weight I would gain. Because there's no air to buoy me up and decrease my weight by a little bit. Fascinating. So do we really weigh what we say we weigh? Or if you put us in a vacuum, we'd weigh a little bit more. So what's our true weight? Oh, I don't want to think about it. Number, where are we? Number 24. On a sense of balance, weigh an empty, flat, thin plastic bag. Then fill it with air and weigh it again. Is there a difference? Well, you're filling the bag with air that has the same density as the air around it. So you're displacing more air now as the bag expands, but you're also adding the weight of the air inside it. So yes, you're increasing the buoyant force, but you're also increasing the bag's weight. Guess what happens? They cancel. It's just like having a water balloon in a swimming pool. It all cancels. So no, there'd be no difference in weight. No difference in weight. 25. 25. I've, oh, it's embarrassing. About 10 years ago, 9 years ago I think, our family went on a camping trip from here all the way to Key West and back again, camping all the way. Quite an experience. How many campsites we had to stop in during that trip, I do not remember. But we went all the way to Key West. And I don't think it was in Key West, it was in one of the other Florida Keys where we stopped for a day or two. And we went on a glass-bottom boat. We were going to snorkel, but the weather was too rough and I was too seasick and we didn't do any snorkeling. But there was a time when we had some snorkeling equipment we bought. And we were going to snorkel on our own, just in some shallow water at a beach someplace. I tried it. No, snorkeling ain't for me. I tried it like for 10 seconds and gave up, said, no, I'm not doing this. So I cannot speak from experience. But I am told, and I believe it, I know it has to be true, that when you're snorkeling, it's a little harder to breathe. Why would it be harder to breathe? Because you are under the water by a little bit, and you've got all this water pressure squeezing on you. But you're breathing through a tube that's connected to normal atmospheric pressure out here. So you've got a normal 15 pounds per square inch of pressure going down that tube into your lungs, but you now have more than 15 pounds per square inch squeezing on your body. We're not used to that. And you have to use more muscle strength to expand your lungs against all that extra pressure that's trying to squeeze your lungs back together again. And so it's a little harder to breathe, and you'll get tired of breathing like that rather quickly, so I'm told. What if you go down about 2 meters, as he says? Will you get down about 2 meters? There's going to be so much water pressure squishing your lungs together that you'll be able to breathe out with no problem. But you're not going to be able to breathe in at all. You're going to die. Yeah, you're attached to the outside air. But the outside air is only 15 pounds per square inch. Who knows how much pressure you have on your lungs the other direction? There's a huge net force trying to push the air out of your lungs. You cannot fight against that. You're not strong enough. I wonder if any of you watching this video have ever actually tried that. What? Yeah. Have you ever, you've got a pool in your backyard, and there's a garden hose laying around, and you're a little nasty, devious, little mean kid, and you say to yourself, I'm going to pull a trick on my parents. I'm going to stick a garden hose in my mouth, and I'm going to go down to the bottom pool, and I'm going to lay there, and I'm just going to wait for my parents to find me. They'll think I drowned. Yeah, real funny. Well, what happens is you put that hose in your mouth, you get into the water, and you start breathing. Hey, it's working. Until you get down a couple of feet, or maybe 3 feet, or maybe 4 feet, and all of a sudden you realize, I can't, it's not working. I can't breathe. I can breathe out, but I can't breathe in. And in a panic, you go back to the surface and say, what went wrong? Too much pressure under the water on your lungs. That's why scuba divers have those tanks. Those tanks are pressurized air. And I don't know how the regulator works, that thing they stick in their mouth. I have no idea how it works. Or is the regulator back here? No, I think the regulator, I don't know. But the regulator is designed to take the high pressure in the tanks and match it to the pressure of the surrounding water as you go down deeper. The deeper you go, the more pressure the tank supplies. So the pressure going in equals the pressure on the outside, and you can continue to breathe. Deep sea divers, the same thing. There's a boat up at the top on the water that has an air pump that's forcing air at high pressure down the hose, down to you as you're walking around on the bottom of the ocean. You can still breathe because they're sending high pressure air down that tube to you to match the pressure of the surrounding water. If that pump up there runs out of gas, blah, 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 you're in deep trouble. Literally deep trouble. Moving on. Number, are we going too slowly? I don't know. Number 26, why does the weight of an object in air differ from its weight in a vacuum? Hey, we already talked about that. Good, we can move on. Number 27 was not assigned, but 27 is so cool. You've got to try this sometime. This is like a requirement. I'll give you an F for the course if you don't try this sometime. Take a helium balloon in your car. Windows closed, sunroof closed. Probably best if you tie it to, maybe if you got a brake handle here, maybe tie it to the brake handle. Try not to let it get too much in your way while you're driving. But suspend that balloon someplace nearby. Here's the cool thing. You remember the accelerometer, which I didn't think to bring down here with me. It's still upstairs. That accelerometer, that jar with the green floaty thing, and as I went in circles, we saw it leaning toward the center of the circle. Or if I move it like this, it actually moved in the direction, it leaned in the direction of the acceleration. This helium balloon will do precisely the same thing in a car. If you're sitting in your car, balloon's beside you, you hit the gas, you would think, oh, the balloon will stay behind. No. The balloon is going to move toward the front of the car when you accelerate, believe it or not. Why is that? As you accelerate, the air in the car is trying to stay behind, right? That's causing the air in the back end of the car to be a little more dense than the air in the front of the car. Guess where the balloon's going to go? Toward the area of less dense air. It's going to go forward. You hit the brakes, you get thrown forward, while the balloon, believe it or not, goes backward. When turning, you turn to the right, you feel yourself being thrown to the left, but the balloon is going to move to the right in the direction of your turn. It's really cool. It actually works. Try it sometime. No, you cannot use my balloon because you can't get near me to get it from me. So there. Where are we now? Number 28. Would a bottle of helium gas weigh more or less than an identical bottle filled with air at the same pressure? Well, the bottle with air will weigh more because air has weight. Air has more weight than helium. That's simple. But what if you had an identical bottle with the air pumped out? A very hefty bottle capable of surviving the air pressure from the outside. You take out all the air. Would it weigh more or less than a container full of helium? It'll weigh less because helium has weight. So the helium weighs more than a vacuum. So your vacuum-filled bottle will weigh less than a helium. Well, then why doesn't the vacuum bottle float up? We've discussed this before. If you have a bottle strong enough to withstand the air pressure while there's a vacuum inside, that bottle is going to have to be really tough. And if that bottle's that tough, it's going to be heavy. It's going to be far heavier than the displaced air. So no, that bottle is not going to float. Neither can Bambi fly. That's another story altogether. Moving on to number. Okay, where am I? I don't know. Number 32. The gas pressure inside an inflated rubber balloon is always greater than the air pressure outside. My inflated rubber balloon, not Mylar. Mylar's different. I have a rubber balloon. There it is. My balloon from the last time, or the time before the last time, whatever. Okay. Why is the air pressure inside this balloon always going to be greater than the air pressure on the outside? Simply because the balloon itself, the latex, is trying to shrink, right? That's what rubber does. It wants to try to shrink. It wants to contract. So the contracting of the rubber is squeezing the air inside into a somewhat smaller package. That's all there is to it. The balloon itself, the latex, the rubber of the balloon, is trying to contract and squeezing the air into a smaller package. That is all there is to that. Number. Oh, and by the way, that's not true of Mylar. In fact, this guy is kind of losing some of his helium. He must have a small leak. getting kind of squishy. Mylar is different because Mylar doesn't stretch. No stretching involved here, so that's not going to be the case with the Mylar. The air out here is going to be equal in pressure to the helium inside the Mylar. Interesting difference between the two. What's the point of Mylar balloons? Well, you know that the helium, if I fill this with helium, the helium can actually sneak out through pores in the latex. And it doesn't take too long before that helium balloon shrinks down to nothing. It's not escaping through there, it's escaping through pores, microscopic pores in the latex itself. Mylar doesn't have those microscopic pores. Mylar, the surface is solid. The helium cannot escape. You can have a Mylar balloon that lasts for like years. But if it has a small leak in it, which this one apparently does, it will eventually shrink. But I've had this balloon since Sunday. This is now Tuesday and it's still doing pretty well. That would not happen with a latex balloon. Moving on to number 36. Would a helium-filled balloon rise in the atmosphere of a rotating space habitat? Let's make a long story short. In a rotating space habitat where you have artificial gravity, as the air is being thrown out to the outer rim of this thing, the air near the floor is going to be more dense. The balloon is going to float away from the more dense air toward the center of the rotating habitat. In other words, if I'm in a rotating space station right now walking around and I release a helium balloon, it's going to go up. What is up? Up is toward the center of the rotation. It's good. It'll work. It'll work. Just like it works on Earth. 37. The force of the atmosphere at sea level against the outside of a 10 square meter store window is about 1,000,000 newtons. Good grief. Why does this not shatter the window? Very simply because you might have 10 I lost it now. You might have 1,000,000 newtons of force on one side, but guess what you got on the other side? Exactly the same amount. The pressures are equal. So it doesn't break, of course. Number 38. Why does a fire in a fireplace burn more briskly on a windy day? Ooh, cool. You got your house sitting here. Okay. You got a chimney. Goes down to the fireplace inside the house. Okay. When the wind blows, the wind goes across the top of the chimney. That fast-moving air going across the top of the chimney creates low pressure here. Guess what the normal pressure in your house is going to do when it encounters the low pressure across the top of the chimney? It's going to go right up that chimney and try to go from the high pressure area to the low pressure area. It's going to go right up the chimney, and that additional air flowing across the fire is going to make it flare up even better. Same thing as the atomizer that we talked about in the last video of the chapter. Number, trying to go fairly quickly here so I don't hold you up too long. Number 41. When a steadily flowing gas flows from a large diameter pipe to a smaller diameter pipe, what happens to its speed? We've discussed that before. It will speed up. What happens to its pressure? Its internal pressure actually gets lower. We're not going to beat a dead horse here. And what happens to the spacing between streamlines? Spacing, what does that mean? Spacing between streamlines. The streamlines refer to these things, these lines of the stream. Well, the spacing between streamlines gets closer as you go into that constricted space, but the pressure actually gets lower. Now, by the way, we're not talking about the pressure when it comes out this hose and hits you. We're not talking about how hard it hits you. We're talking about the pressure inside the liquid will be less. We move on to number 44. When a jet plane is cruising into high altitude, the flight attendants have to have more of a hill to climb as they walk forward from the yeah, you know what I mean. I'm trying to rush too much. Yep. The problem is when the plane is flying at high altitudes, there's less air. Because there's less air, it flies more like this, because it needs to have more air molecules hitting it to help keep it up. When it's down lower, there's more air to hit it and keep it up. Up high altitudes, there's less air. It has to fly at more of an angle to get enough force under here to hold it up in place. Therefore, the flight attendants actually have to walk uphill a bit from the back of the plane to the front of the plane when they're at high altitude. Interesting way to get some exercise. 45. Let's see. What physics principle underlies these three observations? When passing an oncoming truck on a highway, your car tends to sway toward the truck. Have you ever noticed that? It's a little bit unnerving. That's what we're going. Unnerving. Or the canvas roof of a convertible automobile bulges upward when the car is traveling at high speeds. Or the windows of older trains sometimes break when high-speed trains pass by on the next track. Let me give you an example to help illustrate this. Car I had before my blessed Miata was a Nissan NX 2000. That's it. It's been a long time. My Nissan NX 2000 was a beautiful car. It was a true sports car. It's a pretty cool thing. But it was had a T-top. You could take off the panels and you've got the T in the middle. You got a T-top. So it's kind of like a convertible. It was an old car. I bought it used, and it had terrible seats. So I got these seat covers for it. Well, they were cheap seat covers. You just kind of stretch them over there. I noticed, it's kind of embarrassing. You're going down the road, feeling cool. You're in your Nissan NX 2000, T-top, going down the road, cruising, waving through the roof, you know, as you go. And I looked beside me, and that silly seat cover was ballooning up, like it just looked awfully silly. Ballooning way up. Why? Because you've got all this air moving through the inside of the car as you're going down the highway, so that moving air has less pressure. But under the seat cover, the air is not moving. You've got normal pressure, so the normal higher pressure is pushing out against the low pressure inside the car from the moving air, making that seat cover bow out, looking really silly. I've seen the same thing with loose convertible tops, where the convertible top will actually kind of rise up as you're going down the highway. Lower pressure outside from the moving air, high pressure inside because the air is not moving. It bows up. Number. Oh, and what's the principle? Don't forget the name for it. It's the Bernoulli principle, named after a guy named Bernoulli. Yes. 48. No, we didn't assign 48. Did I give you the problems? I think I did. If I didn't, I should have. Page 288. A couple of problems that are significant here. We could look at a lot of them, but we're just going to look at two of them. Page 288, problem number 1. What change in pressure occurs in a party balloon that is squeezed to 1/3 of its volume? Well, if you squeeze it to 1/3 of its volume, the internal pressure is going to be 3 times as much. Pretty simple. 1/3 the volume, 3 times the pressure. Let's see. If you don't let the temperature change, it's going to want to heat up, so you have to kind of fan it to keep it cooled down. If you keep the temperature the same, at 1/3 the size, you'll have 3 times the pressure. Number 2, air in a cylinder is compressed to 1/10 of its original volume. Wow, with no change in temperature. That's going to get hot. You ever use a bike pump? You notice what happens to the pump itself? It starts getting hot. Why? Because as you compress the gas heats up, and you can feel the difference. Likewise, you take an aerosol can and spray it. If you spray it long enough, have you noticed what happens? The can gets really cold because the air inside, the gas inside, is allowed to expand and it cools off. Well, anyway, in this case, you're pumping this, squeezing this air into 1/10 the size. If you squeeze it to 1/10 its size and keep it from getting too hot by cooling it off as you go and keep the temperature constant, as you squeeze it to 1/10 its size, what happens to the pressure? Yes, 10 times the pressure. And it's as simple as that. Okay, folks, now that we've gone through the exercises, you can expect to shortly hereafter get the test emailed to your parents. Then your parents will print the test. They will hand it to you. They will proctor the taking of the test. They will then sign the test that they proctored it. then they will take pictures of it or scan it and email it back to me. Very simple process. So that'll be happening very soon. All right, and that's it for now. Thank you, folks. Be sure to read your emails. Sometimes I throw in details in the emails that I might have forgotten about in the videos, so the emails are still very important all the time. And I hope this one didn't go too long. I have no idea how long it went. What time is it? Ooh, I have to get out of here in 5 minutes. Goodbye, Mr. Leach. Okay, so signing off, and we'll see you next time.